So we're going to continue on with our talk on magnetic fields or magnetic forces, and we're going to look at the magnetic force on a current carrying wire. This is our wire carrying current in this direction here. The wire has length L. We can also think of it as individual charges moving with the drift velocity V. We place this current carrying wire in a magnetic field that's pointing into the page. We know here that delta Q over delta T is equal to I, the current. Rearrange that and we get Q is equal to I delta T. Instead of talking about delta T directly, we're going to talk about velocity and distance. So we know velocity times time is equal to distance. So we have delta T is equal to D, the distance it travels, which is L, the length, divided by V, the velocity. If we take V and put it on this side, we get QV is equal to IL. Now, sometimes you're going to see it in this form, and in other times you're going to see it in this form. I honestly prefer this one because it, feels better, because the idea is one of these quantities has to have a vector notation on it somewhere. So what we have is that, the current has a magnitude and a direction. The length just has a magnitude L. But sometimes you see that bar on the L instead. What it's saying is the current just has a magnitude, but L is a vector in the direction of the current with magnitude equal to the length of the section. So it's essentially the same thing, where we have magnitude of this pointing in this direction. We know that the magnetic force is QV cross B. We know what QV is, so we're going to plug that in here. So we get IL cross B. If, however, we had a bit of a weirder shape, so this is nice because it's like a straight current carrying wire. So if instead we had something that curved like this, we would divide it up into little chunks and we would look at what is the force on each one of these little chunks, like we did in week 2 with like electric forces, right? So you can divide it up. Instead of saying L, you can say ds, a little chunk of length, cross B. So then we have the magnetic force is equal to I, and then we add up all of those little components. We're now going to look at the torque on a current carrying loop. So here we have a loop, current's going in this direction down here. We have a magnetic field coming from the right. What we see is that the net force acting on this loop is 0. How do we know that? Well, we're going to look at this equation for the force, and we're going to remember that this L cross B, so if we have whatever, A cross B is equal to A B sine of theta. So what's the angle between them? If the angle between them is 0, sine of theta is 0. So here, for instance, we have the angle between this wire, this part of the wire, and B, it's 0. So sine of theta is 0. We get 0 here. So then whenever we have the force is 0. So we have no force on this one, no force on this one. On these two, we do have a force. So on 2 and 4, there's a force, but we know that they're at angles of 90 degrees, but you can also say opposite too, right? So we have 90 here and then pointing in the opposite direction. Regardless, the angle here is such that sine of the angle is 1. So then whenever we plug this into this equation, we get I times L, the length, and the length of 2 and 4 here, these wires, is A, times B, the magnitude of the magnetic field. So this is F2 and F4, the magnitudes anyways, and they're in equal and opposite direction. If we were to draw this out in a different way, if you look at this dot here, let's imagine you're looking down this wire, and then you're also looking down this wire. So this is the wire 2 you're looking down, and wire 4 you're looking down. F2 is in this direction, F4 is in this direction, and we can see that they are separated by a distance little b, where little b is just this distance here. So then here, from the center point, this is b over 2, and this is b over 2. Now, if you remember, the torque is equal to F tangential times R, the radius, where only the tangential component of the force contributes to the torque. In this scenario, all of the R, so the radius, is tangential to the force. So all the force is tangential to this radius here. So we're going to have our maximum torque. T max is going to be equal to, here we have F2, which is this one, times b over 2, the radius. So from here to here, b over 2, plus F4, b over 2. Again, B over 2 is here. We know what F2 and F4 are. They're up here, I, A, B. So we add them up together and we get this. Where we have I, little a, which is this distance here, big B, which is a magnetic field, and little b, which is this distance between them. We know that A times B is just equal to the area of this square region, right? So that's the area here. So then T max, the max torque, is IAB, like this. Now what happens if our loop is not perfectly perpendicular like this? So let's say, for instance, we have our loop starts off at this angle here. Now if we say that, well, our force is in this direction, we want to know how much of that loop is actually perpendicular to that force. So to do that, we need to figure out what is the magnitude down here. So in red, what is that length? And what we see is if we define theta to be this is B over 2, this is B over 2 sine theta. So then the torque is equal to F2, B over 2 sine theta, plus F4, B over 2 sine theta. Similar thing, we rewrite it a little bit and we get A, B, B sine theta, where A times B is the area again. So we get this, IAB sine theta. This is the same thing as this here, because remember, A cross B is AB sine theta. So what we say is that in general, the torque is going to be equal to I, the current, times, and then we have A cross B, where A is the area vector pointing in a certain direction, and then B is our magnetic field. We're going to define a new term here. This is the magnetic dipole moment. Mu is equal to I times A. So it's a current, and then the area is going in a certain direction. If we take this definition, plug it back in here, we get torque is equal to mu cross B. I should also say that here, this is the last thing of the section where we define the potential energy of a system to be the magnetic moment in a magnetic field. So here we have potential energy, the magnetic potential energy. This is the magnetic dipole moment dotted with the magnetic field. And that's about it. In the next videos, we're going to actually do some problems.